Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying, right? Just let that sink in for a second. That genuinely chilling thought from sci-fi legend Arthur C. Clarke perfectly sets the stage for our mind-expanding journey today. Welcome to today's Explainer, everyone. We're embarking on an incredible quest to shatter what astronomer Carl Sagan famously called carbon chauvinism. You know, that stubborn idea that life out in the cosmos has to look exactly like us. Together, we're going to explore some radically different biochemistries, dive into wildly speculative alien ecosystems, and confront the ultimate cosmic puzzle, the Fermi paradox. If you're fascinated by the absolute boundaries of what's biologically and physically possible in our universe, well, you're in exactly the right place. Okay, let's dive into this. Here's our roadmap for the Explainer. We'll start with the universal recipe for life. Check out superhabitable worlds and exomoons, and then break the biological rules entirely. After that, we'll visit some bizarre alien ecosystems, move on to the search for giants, and finally ask the big one: where is everybody? Part 1. The universal recipe for life. So, to get the whole biological engine running, nature actually relies on a surprisingly simple set of baseline conditions. Step 1 is energy. You just need the Goldilocks amount, right? Not too much to fry you, not too little to freeze you. Think along the lines of gentle sunlight or the steady geothermal heat you'd find at deep-sea vents. Step 2, heavy elements. Life is essentially a chemical package, so you need a good diversity of atoms that were forged in the cores of dead exploding stars. Stuff like carbon, oxygen, and sulfur. And step 3 is liquid water. Liquids are literally the perfect medium because atoms can just cruise around, bump into each other, and link up to form complex molecules. In a gas, they just fly apart, and in a solid, they're completely stuck. Now, the crucial takeaway here is that this simple recipe might be incredibly common. I mean, look at this staggering number, 100 quintillion. That is the estimated number of potentially habitable planets across the entire observable universe. To put that into perspective, in our Milky Way galaxy alone, we're talking about roughly 50 billion Earth-like worlds sitting right in their star's habitable zone. There are literally more habitable Earth-mass planets out there than there are grains of sand on every single beach on our planet. Part 2. Superhabitable worlds and exomoons. We definitely have this habit of thinking our sun is the ultimate gold standard for life, but honestly, we're kind of in the cosmic minority. Our sun is a G-type star, which only makes up about 7% of stars. The vast majority, roughly 75%, are M dwarfs. The catch with M dwarfs is that they produce these violent, deadly solar flares. But check out that 9% slice, the K-type stars. These orange dwarfs are slightly cooler than our sun, sure, but they burn much longer and are way more stable. A planet orbiting a K-type star could remain perfectly habitable for billions of years longer than Earth, which gives evolution a massive head start. So what would a super habitable, better than Earth world actually look like? Well, it'd probably be about twice Earth's mass with 20% higher gravity. That extra gravity allows it to hold on to a much denser atmosphere, packed with oxygen and greenhouse gases. And instead of vast, barren continents, you'd likely see flatter topography dominated by these sprawling archipelago oceans. Take the speculative twin star world called Eden, for example. Fueled by two suns, its atmosphere sits at a staggering 40% oxygen. An environment like that could support towering flora and massive grazers, maybe even locked in a survival dance with symbiotic, mind-controlling fungi. It would just be an absolute paradise of biodiversity. And this brilliantly illustrates why we shouldn't limit our search just to planets. Astronomers estimate there could be 100 trillion exomoons in our galaxy alone. That's 100 times the number of planets. Even if these moons orbit giant gas planets way out in the freezing dark, far beyond the traditional habitable zone, the lurching push and pull of their host planet's gravity creates intense internal tidal heating. That friction can literally melt ice from the inside out, creating hidden subsurface oceans full of life-giving hydrothermal vents. It's exactly what we suspect is happening right now in our own backyard on Jupiter's Europa or Saturn's Enceladus. Part 3. Breaking the biological rules. Okay, let's toss out the rulebook for a second. What happens when we completely abandon our reliance on carbon? We all know carbon is the versatile champion of life on Earth. It forms these incredibly strong four-way bonds, creating the long, stable molecular chains that complex life needs. But look at silicon. It sits right below carbon on the periodic table and can also form four-way bonds. Now, its bonds are weaker, and here's the kicker. In the presence of oxygen, silicon actually turns into solid rock. Not great. But On frigid, oxygen-free worlds, silicon could totally thrive. You could have silicon-based life with ultra-slow metabolisms operating in extreme cold, or maybe even a shadow biosphere existing deep within molten silicate rock right beneath our feet. The same rule-breaking applies to our favorite liquid. Water is fantastic, don't get me wrong, but it freezes and boils way too easily for much of the universe. Consider liquid methane and ammonia. On freezing bodies like Saturn's moon Titan, which, by the way, actually has real weather cycles and lakes of liquid methane, temperatures are way below zero. Under those conditions, totally bizarre alternative biochemistries could emerge. Instead of water-based cellular structures, life might utilize flexible, liposome-like membranes called azotosomes that function perfectly in sub-zero methane seas.
Part 4. Bizarre Alien Ecosystems. Let's paint a picture of what these radical chemical rules could actually look like in practice. Imagine the eye of Ipa, a tidally locked planet orbiting a dim red dwarf star. One side is eternally scorching, the other permanently frozen in darkness. But right on the boundary between the two, an eternal storm rages over a shallow ocean. Because the red dwarf's light is so incredibly weak, the kelp-like forests here don't bother evolving to be green. They evolve to be pitch black, absorbing absolutely every scrap of infrared energy they can. And in these murky, storm-churned waters, creatures don't even evolve eyes. Instead, blind predators navigate and hunt by interpreting a chaotic cacophony of underwater sound and texture.
Next up, picture Nimbus. This is a hot gas giant, completely devoid of a solid surface. Survival here is 100% about staying buoyant. Meet the sky whales, skyscraper-sized living balloons floating in the thick, superheated atmosphere. They heat up trapped gases within their wafer-thin bodies just to achieve lift. They just drift effortlessly, filtering microscopic cloud plankton right out of the air and converting it into an energy-dense nectar. Oh, and they do all this while being relentlessly hunted by rocket-propelled vampiric jet squids. Now let's swing to the complete opposite extreme. Welcome to Monior, a frigid moon orbiting a brown dwarf star that puts out a monstrous magnetic field. It is so brutally cold here that life relies entirely on liquid ammonia. But what's truly spectacular is how life utilizes the planet's ambient magnetism. Evolution here birthed skaters. Think of them as snail-like creatures zooming across the ice on electrically conductive stalks that act like magnetic kites. And hovering above them are sky flowers, saturated with magnetic minerals, literally levitating off the ground, straining to catch just a few fleeting rays of starlight in the freezing dark.
Part 5. The Search for Giants. So, moving beyond microbial and animal life, how do we hunt for advanced, intelligent alien civilizations? To understand these giants, we use the Kardashev scale. It's a theoretical framework for classifying alien super-civilizations based on their staggering energy consumption. Step 1 is a Type 1 civilization, which has successfully harnessed all the energy available on its home planet. Step 2, a Type 2, harnesses the entire energy output of its host star. And Step 3 is a Type 3 civilization, a society that commands the energy of its entire galaxy. For a little humbling context, humanity hasn't even reached Type 1 yet.
So, how do we spot these technological titans? We look for their techno-signatures. We are talking about scanning the night sky for high-powered laser pulse beacons acting as galactic lighthouses, or detecting ghostly neutrino messages traveling straight through solid planets. We might spot the lingering atmospheric pollution of long-dead civilizations, like chlorofluorocarbons. We could even detect the dimming starlight and waste heat caused by artificial Dyson swarms blocking their host sun, or star-lifting gas trails left behind by colossal starships hitting the brakes at near-light speed.
Part 6. Where is everybody?
Which brings us face-to-face with the ultimate philosophical puzzle, the Fermi paradox. If the universe is so vast and so old, where is the great silence coming from? The potential solutions are genuinely terrifying. It might simply be that space is just too enormously vast for feasible communication. Or maybe civilizations hit great filters, technological or biological hurdles that cause them to self-destruct before they can reach out. There's also the chilling dark forest hypothesis, which suggests everyone is deliberately hiding to avoid roaming galactic superpredators. Or, quite possibly, we are simply the very first to look up. Now, what's really interesting about the cosmic timeline is just how much it shifts our perspective. The Big Bang happened 13.8 billion years ago. We often feel like we're late to the party, right? But look at the future. The last stars, those stable red dwarfs we talked about, won't die out for another 100 trillion years. They're going to provide stable homes for life for absolute eons. In the grand cosmic symphony, we are merely the opening melody. We are standing at the absolute dawn of time. There's this profound thought from anthropologist Lauren Isley: one does not meet oneself until one catches the reflection from an eye other than human. Impartially speaking, whether we eventually find intelligent life staring back at us or whether we confirm our absolute, profound solitude in the cosmos, the implications are staggering. Finding no one else places an immense, almost sacred responsibility right on our shoulders to preserve the fragile flame of consciousness. So, we're going to leave you with this final provocative thought. If the ingredients for life are everywhere, where is everybody? And if we truly are alone as the universe's opening melody, what will we choose to become? Thank you for exploring the cosmos with us in today's Explainer. Keep wondering, keep looking up, and let this knowledge fuel your curiosity. Until next time.